Imagine you are a triage nurse stepping into just a chaotic emergency room.
Which is pretty standard, honestly.
Right, totally standard. And you glance at two different patient charts. Patient A has a core body temperature of, say, 96 degrees.
Okay.
And patient B has a core temperature of 101 degrees. Which one is in more danger?
That's a great question.
Yeah, because in clinical medicine, just like in high-level data science, the most important question isn't necessarily whether a number is going up or down. Often, the only question that actually matters is just how far are you from zero.
That is, that is just the perfect way to frame it. We are so conditioned to think of positive as good and negative as bad. Or, up is better than down.
Right, like money in a bank account.
Exactly. But when a system is highly calibrated, whether that's a human body or like a predictive algorithm, any deviation from the baseline is a problem. The direction of that deviation is completely secondary to the actual magnitude of it.
Well, welcome to another deep dive. If you're joining us today, there is a very good chance you are gearing up for a nursing entrance exam. So, maybe the TEAS or the HESI.
Or maybe you're just insanely curious about how the math we all grown through in middle school actually quietly runs the modern world.
Yeah, totally. So today's mission is to take this massive stack of sources we've got, and it covers everything from math history to clinical application notes, and demystify one specific vital concept, which is absolute value.
It is a concept that seems incredibly basic on a chalkboard, right? Just two little vertical lines on a page.
Yeah, just those straight bars.
Right. But it has this surprising depth, and it trips up brilliant students and seasoned professionals alike.
Because our angle today is that absolute value is not just some, abstract algebra rule. It is the mathematical backbone of everything we just talked about. It is purely and simply distance from zero.
Distance from zero, exactly.
And to really grasp how this applies to clinical work and beyond, we first have to sort of strip away the confusion of its textbook definition. Fundamentally, we are trying to answer a single question for you today. How far did you travel, completely ignoring the direction you took to get there?
Yeah, and direction really is the key word to drop there. Every real number you encounter gives you two distinct pieces of information.
Okay, what are they?
Well, it gives you magnitude, which is how big it is, and it gives you direction, which is whether it points left or right of zero on a number line.
Got it.
Absolute value basically acts like a filter. It just throws away the direction and strictly preserves the magnitude.
So, if you're looking at the number 7 and the number -7, they both sit exactly 7 units from zero.
Right.
One went right, one went left. But if you were tracking your steps on a smartwatch, the distance walk is identical in both scenarios. The absolute value of 7 is 7, and the absolute value of -7 is also 7.
That physical analogy is spot on. But unfortunately, that intuitive idea of a smartwatch tracking steps gets completely lost when students open their pre-algebra textbooks.
Okay, let's unpack this. Because I know the formal piecewise definition they give you on these exams is just incredibly confusing to look at.
Oh, it's terrible.
Let me actually read it out loud for you. It says the absolute value of A equals A when A is greater than or equal to 0. Fine, I get that.
Makes sense.
But then the second line says the absolute value of A equals negative, literally a minus sign in front of the A when A is less than 0. Wait, that second line looks like it produces a negative number.
Yeah.
Doesn't that completely contradict the whole distance is never negative rule?
I completely understand why it looks that way. And honestly, that single line of notation trips up more students than almost anything else in early algebra.
It's so counterintuitive.
It is. The visual trick here is that we associate the minus sign with the word negative, but we have to remember what a variable is actually doing. It's just an empty box waiting for a number.
Like a placeholder.
Exactly like a placeholder. If a is already a negative number, let's say a sev is -7, then the formula tells you to take the negative of whatever's in that box.
Right.
So you are taking the negative of -7.
So it's a negative of a negative.
Minus -7 mathematically becomes +7. The result is positive.
That makes so much sense when you say it like that.
Yeah, the absolute value rule isn't actually flip the sign, which is how it's often poorly taught in crowded classrooms.
Yeah, I definitely heard flip the sign in high school.
We all did. But
Yeah.
the actual rule is produce the non-negative twin of the number. If the number is already positive or 0, you do nothing. If the number is negative, you give me its positive twin.
I love that phrasing, the non-negative twin. It takes the mechanical math and turns it into a concrete identity.
What's fascinating here is that while that piecewise definition the one with the confusing minus sign is what you have to compute with on a written test, mathematicians actually consider a second, broader definition to be far more fundamental.
Hmm.
Yeah. They define absolute value strictly as distance between 2 points. So the absolute value of A minus B is just the physical distance between A and B on a line.
Oh, because that frees you from always having to measure from zero. Like you can just measure the distance between any two things.
It makes the math incredibly versatile. That distance-based framing generalizes cleanly into geometry, into statistics, and into much higher mathematics.
Right.
The piecewise textbook definition is really just the mechanical engine under the hood that calculates that distance for us.
So if we know absolute value measures magnitude instead of direction, and it works as this like universal measuring tape, how does that actually look in the real world? Let's take it off the paper.
Good idea.
There was a striking geographical anchor in the sources that really visualizes magnitude versus direction, the Death Valley versus Denver example.
Oh, yeah, that is a phenomenal way to see this in action. Because we use sea level as our zero elevation.
Right, and Badwater Basin in Death Valley sits at negative 282 feet. It's 282 feet below sea level. Now Denver, the mile-high city, is at positive 5,280 feet.
Right.
If you want to know which location is further from sea level, you don't care about the positive or negative sign. You aren't digging a hole or climbing a mountain. You just want the raw distance.
Exactly.
You're asking for the absolute value of negative 282 versus the absolute value of 5,280.
Which leaves you comparing 282 against 5,280. Denver obviously wins by a massive margin.
It's big time.
The fact that Denver's elevation number is, quote, more positive and Death Valley's is more negative is totally irrelevant to the question of its absolute distance from zero. The plus or minus sign merely acted as a directional compass, above or below.
Yeah.
The absolute value gave you the actual distance traveled from the baseline.
So what does this all mean for you listening right now? Let's take that exact mountain and valley logic and bring it straight to the clinical application. Let's go back to that triage nurse evaluating body temperature from our intro.
Normal core body temperature is generally cited as 98.6 degrees Fahrenheit or 37 degrees Celsius. That is the clinical sea level.
That's our zero.
That is our zero.
And when you evaluate a patient, you aren't just looking at whether a temperature is higher or lower than 98.6. You have to compute the magnitude of the deviation.
Exactly.
So let's say patient A comes in at 95.8 degrees and patient B comes in at 101.4 degrees.
A nurse's mental math is essentially taking the measured temperature, subtracting 98.6, and finding the absolute value of that difference.
Okay, so let's walk through that.
Sure. For patient A, 95.8 minus 98.6 is negative 2.8. But we take the absolute value, so the deviation is 2.8 degrees.
Right.
And for patient B, 101.4 minus 98.6 is a positive 2.8. The deviation is identical.
They are both exactly 2.8 degrees away from normal. And in a clinical setting, both of those deviations are highly concerning.
Very concerning.
Like, one might indicate hypothermia and shock, the other a severe infection.
Yeah.
But the alarm bells ring because of the magnitude, the absolute distance from normal. That makes absolute value the invisible engine of almost all nursing-adjacent math.
It really does. It extends to everything a clinician monitors. Blood pressure, potassium levels, medication dosages.
Wow, yeah.
If a patient's lithium level is dangerously far from the therapeutic range, the absolute distance from normal is what dictates the urgency of the intervention. And, it is true across non-medical disciplines, too.
Oh, like what?
Well, political polling uses margins of error. When you hear accurate within 3 points, that is an absolute value statement.
Oh, I never thought of it that way.
Yeah. Or a bank account overdrawn by $40 versus a surplus of $40. Both require exactly $40 of activity to get back to zero.
Okay, so if absolute value is just this highly intuitive, universal concept of measuring how far off something is, why do we write it with such specific, rigid notation? Those two harsh, uncompromising vertical bars?
That's a great question.
Because that question actually takes us back centuries into the history of the math itself, based on our sources.
The history of mathematical notation is rarely a straight line, and the evolution of those vertical bars is just a perfect example of a simple idea being forged in a very complex fire.
Yeah. Tracing the lineage in our sources was wildly surprising to me. We actually start with René Descartes back in 1637 in his famous work, La Géométrie.
Right.
He was working with complex algebraic equations, and he started doing something highly unusual for the time. He treated coefficients in a sign-blind way.
Exactly.
He was looking at a term's absolute raw size completely separately from whether it was being added or subtracted in the equation.
And historians largely regard Descartes' approach as the early conceptual ancestor of absolute value. He recognized that magnitude had a mathematical utility independent of direction, even though, he wasn't defining it as a standalone function yet.
The concept had to evolve, and it did. In 1806, with a mathematician named Jean-Robert Argand. And Argand was dealing with a totally different beast, complex numbers.
Complex numbers involve the square root of -1, which is an imaginary number. Argand had these incredible numbers that work beautifully in theoretical algebra, but they had a massive problem.
Oh, what is
They
it?
had no obvious size. On a standard one-dimensional number line, you can easily see how big a number is. But a complex number like 3 plus 4i doesn't sit on a standard number line at all.
No, it sits on a 2D plane, it has a horizontal part and a vertical part. So Argand introduces this concept called the module, or modulus, to measure their distance from the origin on that flat graph.
Right.
He just used the good old Pythagorean theorem. 3 squared is 9, 4 squared is 16, 9 plus 16 equals 25. The square root of 25 is 5, boom.
Yep. Boom.
No sign flipping, just pure geometry to find the absolute physical distance from the center.
That brilliance expanded absolute value beyond a simple left-right number line into multiple dimensions. Today, in higher dimensional physics and engineering, we actually call it a norm. But it is the exact same core idea Argand was playing with magnitude without direction.
But Argand didn't give us the vertical bars. That invention belongs to Carl Weierstrass, a German mathematician who lived from 1815 to 1897. They literally call him the father of modern analysis.
And if we connect this to the bigger picture, Weierstrass was not teaching middle school arithmetic. He was operating at the absolute bleeding edge of 19th century mathematics.
Yeah, big time.
He was building the rigorous epsilon-delta foundations for calculus.
Which is incredibly dense stuff.
Incredibly dense. To write airtight, flawless mathematical proofs about limits and continuity, Weierstrass needed a compact, unambiguous notation.
Right.
He needed a symbol to express that the distance between variable x and point A is less than a tiny margin called delta. So he wrote the absolute value of x minus a is less than delta using those two vertical bars. The notation was so effective and clean that it permanently stuck.
And here is the delightful irony of this entire deep dive for you listeners who are taking entrance exams right now.
This is good.
The exact same two vertical bars that you are sweating over to solve a simple equation, like the absolute value of x minus 4 equals 9 on a TEAS test, those bars were literally invented to rigorize the most advanced, complex branches of 19th century theoretical calculus.
It really is a profound piece of mathematical shorthand. But because Weierstrass designed this notation for strict airtight proofs, the rules for manipulating it on modern exams are incredibly rigid.
You can't just play around with it.
Exactly. You cannot casually bend the rules of a symbol designed for absolute precision.
Which naturally explains why test makers love using that rigidity to build traps for students. Let's look at how a student might misuse this rigidity in an exam setting. The most famous trap in our prep sources is the no solution trap.
It is everywhere on standardized tests. A student is given an equation. The absolute value of x minus 5 equals -3.
And the student, probably running on adrenaline and memorized procedures, mechanically splits it into two cases. They write x minus 5 equals -3, x minus 5 equals +3. They solve for x, get two distinct numbers, bubble in their multiple choice answer, and move on.
Happens all the time.
But let me push back on behalf of the listener here. If I do the algebra on paper and the math mechanically spits out two numbers, why can't I just use them? Why is this a trap?
It's a trap because it tests meaning, not just mechanics. The test maker is checking to see if you remember what the bars actually represent. Go back to our very first principle. Absolute value is distance. Can a distance ever be negative?
No. I can't walk -3 miles to the grocery store.
Precisely. An absolute value expression, once isolated, can never equal a negative number. When you see the absolute value of x minus 5 equals -3, the correct move is to instantly recognize it has no solution.
You just stop.
You stop writing. No further algebra is needed. Test makers put this question in specifically to catch students who are operating on autopilot without understanding the concept of magnitude.
That is a massive time saver. Do not let the mechanical steps blind you to the reality of the math. While we're looking at the exam survival guide, let's clear up a few other major misconceptions from the sources.
Great idea.
First up, the triangle inequality. A lot of people assume you can just distribute the bars. They think the absolute value of A plus B is just the absolute value of A plus the absolute value of B.
Which is a fatal error if the numbers have different signs. Let's use 5 and -3. If you keep them together inside the bars, 5 plus -3 is 2. The absolute value of 2 is 2.
But if you split them up, the absolute value of 5 is 5. The absolute value of -3 is 3. 5 plus 3 is 8. 2 does not equal 8.
No, it doesn't. The combined distance never exceeds the sum of the individual distances.
It's like walking a dog.
Oh.
Yeah, if I walk straight from my house to the hospital, that's one distance. But if my dog drags me to a fire hydrant first, and then we walk to the hospital, the sum of those two separate trips is always going to be longer than the direct path. That's the triangle inequality.
That is a really great way to visualize it.
Thanks.
Now, what about symmetry? Test makers love to present the absolute value of A minus B, and then later in the equation, the absolute value of B minus A. Students waste so much time trying to convert one to the other.
But they are identically equal,
Right.
because of the physical analogy again. The distance from your house to your school is exactly the same as the distance from your school to your house.
Exactly.
Doesn't matter which order you subtract them in inside the vertical bars.
Absolutely. And the final exam pitfall involves square roots. Algebraically, the absolute value of x is identical to the square root of x squared.
Wait, really?
Yeah, if an exam asks you to simplify the square root of x squared, you cannot just write x. If x was -5, squaring it gets you 25, and the square root of 25 is +5.
Oh, I see.
You have to write the absolute value of x to guarantee the output is non-negative.
Man, so we've seen how this traps nursing students on standardized exams. But I have to ask, does this seemingly simple concept ever trip up actual professional mathematicians?
It doesn't just trip them up. The basic visual shape of the absolute value function is the center of an active, highly debated divide in modern data science and machine learning right now.
Here's where it gets really interesting. In statistics, when we want to measure how spread out data is, we normally use standard deviation. And standard deviation relies on squaring the differences from the average.
Right.
But if I have a massive outlier, say, a data point that is 10 units away from normal squaring, it gives it a weight of 100 in my model, doesn't that artificially inflate the panic around a single massive outlier? Is there a way to measure spread that just uses raw distance?
There is, and it's called mean absolute deviation, or MAD. Instead of squaring the errors, MAD uses raw absolute value. It simply finds the average physical distance from the middle. It literally means what it says.
Yeah.
Mean absolute deviation.
And choosing between those two methods, squaring the errors versus taking the absolute value, creates a massive divide in how we program AI.
This raises an important question about how we build predictive models. When statisticians train an algorithm, they have to decide how to penalize the machine for making mistakes.
Okay.
Do you penalize the mistake by its raw absolute value, which is called an L1 penalty, or do you penalize it by squaring the mistake, which is an L2 penalty?
To answer that, the sources brought up the statistician Robert Tibshirani. Back in 1996, he was dealing with data models that had way too many variables. They were clunky and overcomplicated.
Very noisy data.
Exactly. So he introduced a regression technique called lasso. And lasso deliberately uses the absolute value, the L1 penalty, rather than squares.
And the mathematical consequence of that choice is wild.
Yeah.
Think about the geometry. If you graph a squared term like x squared, it forms a smooth curve, a parabola that gently bottoms out at 0.
Like a U-shape.
Right. But if you graph an absolute value, it looks like a harsh, rigid V. It has a sharp, non-smooth corner exactly at 0.
But how does a sharp corner actually change the way an algorithm learns? Like, why does a shape matter?
Think of it like a marble. The squared penalty, the L2 model, is like a marble rolling down a smooth, curved bowl.
Okay.
It rolls back and forth and eventually settles near the bottom. But because of the gentle slope, it almost never perfectly stops at dead center 0. It just gets really close.
Interesting.
The absolute value penalty, the lasso model, is like dropping a marble into a sharp V-groove. It wedges tightly and perfectly at exactly 0.
That is incredible. Because it wedges exactly at 0, lasso regression can push the weight of unhelpful variables to exactly 0. It automatically deletes the useless data from the model.
Exactly.
The smooth curve just shrinks things towards 0, keeping all the clunky variables alive.
A fundamental geometric difference, a sharp corner versus a smooth curve, creates entirely different behaviors in artificial intelligence.
And for you listening right now, wondering why a nursing student should care about lasso regression,
Yeah.
you might never program a machine learning model on the floor of a hospital. But the predictive AI that tell your hospital administrator how many nurses to staff in the ER during flu season.
Or the software that predicts patient readmission rates based on hundreds of complex variables.
Yes, it relies on this exact geometry. It uses the sharp corner of absolute value to filter out the noise and find a signal.
The foundational math always scales up. It is the invisible architecture of the tools you will use every day.
So as we wrap up this deep dive, let's trace the journey we've been on today. We started with René Descartes treating coefficients blindly without their signs.
Quite the rebel.
Then we watched Carl Weierstrass trap those numbers inside rigid vertical bars to prove calculus. We saw how triage nurses use the exact same logic to evaluate patient fever thresholds.
Right.
And finally, we looked at how dropping a marble into the sharp V-groove of absolute value helps modern AI filter out bad data.
And for anyone taking their TEAS or HESI exams this month, remember your 5 golden takeaways. 1, distance is never negative. 2, the absolute value of x gives you the non-negative twin, turning negatives positive but leaving positives alone.
3, an isolated absolute value equation equaling a positive number yields 2 solutions. Equaling 0 yields 1 solution. And equaling a negative yields absolutely no solutions.
4, inequality is split into cases. Less than means your answer is trapped between 2 values. Greater than means your answer points outward beyond them. And 5, distance is perfectly symmetric. The absolute value of a minus b is always the absolute value of b minus a.
A perfect summary.
You know, before we sign off, I think there's one final piece to mull over here, building on that concept of deviation from normal thinking we see in clinical triage.
Oh, I'd love to hear it.
Consider how much of our society is utterly obsessed with directional metrics. We constantly measure our lives by stock market gains versus losses, political left versus right, getting ahead of our peers versus falling behind.
We really do.
We let the plus or minus sign dictate our stress levels. But what if we evaluated the health of our own lives more like a triage nurse evaluates a patient's vitals? What if we measured our success by our absolute distance from a healthy baseline of well-being, regardless of which direction we've strayed?
Wow, that's deep.
Sometimes it's not about whether you are too far left or too far right or moving too fast or too slow. It's simply about recognizing the magnitude of your distance from center and doing the work to get back to 0.
It really is all about that magnitude. When you think about it that way, stepping into the chaotic, muddy waters of medicine or data or just life doesn't require you to always know exactly which direction to go. It just requires you to know where your 0 is and measure honestly from there. Thank you so much for joining us on this deep dive. Whether you're heading into the TEAS, the HESI A2, or just out into the world, tackle it with confidence. We'll see you next time.